We already kind of made this assumption without saying anything about it, but for gravitational forces, we're assuming point masses. We're assuming that the objects are just the point masses with all the mass concentrated at their center of mass, and this works. Turns out this works, and even in cases, and it's not just because they're really far away. Like even with the Earth exerting force on us, we can treat it as a point mass because the Earth is a sphere, and we're chilling out on the surface of the sphere. There's a little person there. And the force that this part of the Earth exerts on us would be this way, but that's exactly canceled out by the there's a force exerted this way from a point over here, and the horizontal components of this cancel out at all. If you take an integral and add up all the forces from all the little pieces, it winds up being just a single force pointing toward the center of mass of the Earth. So it is a good assumption. It works to assume that objects are point masses. Another thing about the law of gravitation that I think I've mentioned before is that we learned that near the surface of the Earth, gravitational force is equal to mg. Well, where that comes from is from plugging in g, this is your mass, times mass of the Earth over radius of the Earth squared, and this g times mass of the Earth times over radius of the Earth squared comes out to be about 9.8. And that's where we get the value of little g. So if you're asked to calculate an acceleration due to gravity at some point, well, that's just little g, but in general, at any point, the acceleration due to gravity is going to be g times mass of the Earth over r squared, where r is the distance to the center of the Earth. Or, it doesn't have to be Earth. It could be on another planet or whatever. Another thing to keep in mind is that this r is distance from the center of the object. So if you're given that a satellite is so far above Earth's surface, then what you plug in here is not going to be the number you're given. It would be the number you're given plus the radius of the Earth. So make sure you keep that in mind. A little bit of history. In 1798, a guy named Cavendish performed an experiment, and your book talks about this on page 385. The setup is a little bit hard to describe, and even reading it and looking at the pictures, it might be difficult to note what's going on. But it was a pretty clever experiment, and using this, he determined the value of g to be 6.754 times 10 to the minus 11th. This is, more than a century after Principia. Remember, Principia was 1666. So more than a century after Newton published Principia, this experimenter got a value of g that's pretty close to what we use in the present day. And this let us calculate the Earth's mass because we already knew the radius of the Earth from other experiments, and they had done a lot of work to measure the value of little g, and so we were able to calculate the mass of the Earth. That was the first calculation of Earth's mass, and comparing the mass and volume of the Earth that led us to the conclusion that the Earth's density was higher than the surface density. They figured out that the density of the Earth was about 5.53 grams per centimeter cubed, while the density near the surface, the density of granite, for example, is about 3 grams per centimeter cubed. And so they came to the conclusion that the Earth is denser as, in further down below the surface, and that led us to investigating the structure of the interior of the Earth, and ultimately to what we now know about the core and the mantle and stuff like that. It arose out of this distinction in the density. On a somewhat related note, the moon, the moon's density is pretty much the same as its surface, and so it's assumed that the moon has a more or less uniform structure all the way through, so no nobody's really taken any time to research what the interior structure of the moon is, because its density is the same as the surface, so it's assumed that it's pretty much the same all the way through.